Exactly. All right, let's go ahead and start. Sorry, I didn't realize 16 wasn't open yet. It's due Thursday at midnight. This is a really quick one, I promise. In the past, I think people finished it in 30 minutes or less. I say that and now it's going to take you all 4 hours or something. Yeah, so all you're doing is labeling things aromatic, anti-aromatic, or you might have a nitrogen, you have to label it basic or non-basic. That's it. Chapter 17 is open, and your exam is when? Tuesday? Or when did I have this one? The 20th, I think? The 20th? Oh, wait. You what? Yeah, that's not about to change. If y'all ever see that, let me know. Okay, so I have the due dates for 16 and 17 up, and I opened up the exam 3 review if you wanted to. Wait, what? Today's the 14th. Yeah, go home and do it now. The midterm, did y'all get that? I sent it out, so just return it by class tomorrow. You can email it or give me a hard copy. I don't care. Okay, sorry about that. I don't think IT will be able to fix the problem in time, so it's easier for me to send you a hard copy. So let's see, what else? The discussion 4 is due next Monday at midnight. Some of you have already started that. Your next exam is Tuesday, and that's right before the break, and I promise you it's a good thing. So then for your break, you don't really have anything, at least for my class, anything to study or anything like that, okay? So I like to give them right before the break, so if I ever give one like right after the break, your exam scores are like at least 10 points below average. So Lab 5 this week is there tomorrow at midnight, and we should cover that material you'll need, most of it today, maybe a little bit tomorrow. But I would say after today's lecture, you should be able to do 95% of it. Then there might be like one other question left that we'll cover tomorrow. Is that okay? And then 6 and 7, that's what I wanted to bring up. So let me come back over here. So Lab 5 is due Thursday at midnight, so tomorrow at midnight. And your midterm exam is due tomorrow by class. 6 and 7 is due Wednesday at midnight. I sent y'all, this might help you too, a revised schedule, and I put on there when labs were due. I sent that out like yesterday or something. Anyway, so it has on there when the saplings are due, when the exams are, and when the labs are due. Like the new. Huh? I just opened it up. The only reason I hadn't, that's what I was going to bring up. I hadn't opened it up. Again, we're having problems with this website. Let's see, is that the lab? Yeah. Okay, So the personal capture echo that I have usually for the lab will only record right now in audio. Okay? And so I was trying to get that fixed before I released it. They worked on it for a while. They can't figure it out, so now they have to actually contact Echo and see what's going on. But I did put the audio on there so you have something. Hopefully it doesn't just start playing. Okay. But the audio is down there so you can at least hear it. And what I did, I talk about different links, like I talk about an image or something like that. This link right here, so for example, Lab 7 amino acids, if you click here, that's sort of the link I'm looking at. And then the sugars here, that's what I'm looking at. So what I would do is click on that link before you listen to the podcast, kind of skim over it at least, get a general idea what it goes over. None of them are very long. This one's like Cliff Notes kind of thing. Cliff Notes, about a page and a half long of a summary of sugars. And the amino acids, it's basically the wiki page for that. Okay, so just kind of skim over that and then listen to the podcast. And I think that'll help a lot. And then you can always pause the podcast and then go pull up that link again to kind of compare. Anyway, that's the best I can do right now. So watch those or listen to those. And if you have any questions, well, let me know. For the most part, the sugars are going over, well, two things. First of all, sugars are, let me open this. You see it okay, a little longer than I thought, but not too long. So sugars here, let me show you like these here. Do you see I have a lot of alcohols? So we're covering alcohols. And then also up here, this is an aldehyde, the CHO. That's a C double bond O with a hydrogen coming off. And then right here, not that one, yeah, that one, is a ketone. So sugars can either be aldose sugars, which means aldehyde sugars. So at the very top up here, you're either going to have an aldehyde or a sugar called a ketose, which is a ketone sugar at the top. Okay, so that's kind of what it covers. So looking at aldehydes and ketones, and you're testing different sugars. I hope you like the remaining labs. You'll actually be doing a little bit of experimentation, testing things that will apply to like biochem. So you're going to be testing carbohydrates, amino acids, enzymes, stuff like that. And I'll show you, hopefully by the end of the lab, you'll see how this applies obviously to biochemistry because it's an amino acid and a sugar, but also to our class. Okay, so that's what this goes over. And then amino acids, it's just the structure of an amino acid. Amino acids are amide groups, so it's a carbonyl with an amine. So yeah, so try those. These are due next Wednesday at midnight. Okay. Now you can get them done before then because I know Wednesday goes into your break. So if you want to get them done before, like usual, you can turn them in before then. So then the only thing coming up for sapling would be 16 and 17. I think that's everything I do. So we have sapling 16, 17, exam on Tuesday, discussion 4, which some of you have already started that, and the labs, and Facebook. And let me let me show you Facebook. Facebook isn't that bad this week. Not that it's ever that bad. I have not graded your Facebook yet. I'll grade those tomorrow, so don't worry if you don't have a grade yet. This week, I want you to find an interesting article, at least interesting to you, and briefly discuss its connection to chiropractic and our biological chemistry. Okay, I know this is going to be on Facebook, so you don't have to write a 10-page narrative or anything like that. But something that, maybe the people who have connected with you, your friends or whoever, will be interested in reading. And you could talk about how this, affects their life and so forth. Does that make sense? Okay. So that's what you need this week. The other thing we need to go over is amino acids. So basically from this point on, we'll learn 2 amino acids a day. The reason is because a lot of students, well, I've been doing this for a while, but a lot of them suggested learning amino acids because in biochemistry, from day 1, he assumes you've already have them memorized. Okay? He's not going to take the time to show you the amino acids or anything like that. Okay? So he assumes you have it down and you understand them for the most part. He'll go over them briefly, but very briefly. So I think it's better that I force you basically to memorize them now. So we'll learn 2 a day, and these will be cumulative. So you'll be tested over these. So for example, on exam 3, which is on Tuesday, you'll be required to know the amino acids we cover up until Monday. So you'll have 6 of them. Okay? And then exam 4, you'll have to know the new amino acids plus the 6 we're learning this time. Okay? So by the end, hopefully you know all of them. So let's go over briefly what is an amino acid. Amino acids have this basic structure like this. There's an alpha carbon. Do you see this is sort of the central carbon where everything is sort of coming off of? Okay, that's called the alpha carbon. And you see off of here we have this functional group here, which is an amine, which is a nitrogen. We call it like NR3. So that could be a nitrogen with 3 carbons or hydrogen. So it's a mixture of carbons and hydrogens. What mixture doesn't matter, okay? Nitrogen with either carbons or hydrogens coming off. Nothing else. This, even though it doesn't look like it, it's a carboxyl group. This is a carboxylic acid without the hydrogen. So it looks like this. So carboxylic acid is like this. And a carboxyl is the same thing, except now that hydrogen is gone. So it's just a negative charge. So it's after a carboxylic acid reacts as an acid. It lost its hydrogen. So notice COO. And so it's abbreviated a lot of times as COO. So if I come over here, you can see the COO. Let's see, what else? This R group right here stands for a carbon group. And this is what makes all your amino acids unique. Okay? They all have this top part right here. This carboxyl group, this amine group, this hydrogen. Every single amino acid has that by definition. But what makes them all different is this R group coming off here. Okay, that's the only thing that's different. So whenever we're looking at amino acids, usually what you're memorizing is that R group. You understand that, yes, they all are like this, and the only thing that's unique is this R group. Zwitterionic, or sometimes called dipolar, this means you have a negative and a positive within the same structure. Okay, dipolar meaning 2. Okay. And the fancy word for that is zwitterionic. So you see you have a negative, it's overall neutral, but it has a negative and a positive within the structure. This carbon is chiral. Remember we did like R and S. If you look, there's 4 different things coming off this alpha carbon. There's an R group, a hydrogen, a carboxyl, and an amine. Okay? So there's D amino acids and L amino acids. When we did R, that is like a D. So R and D go together. And then L and S go together. Why do they use different letters? Because they like to confuse us, okay? But R and D are the same, L and S are the same. Okay, and so the reason they draw this like here, because sometimes when you see an amino acid, sometimes they'll actually draw this as neutral. Sometimes they'll draw it as zwitterionic. Neutral meaning it hasn't reacted yet. Zwitterionic is after it's reacted. So if we look at this, a carboxylic acid, the pKa of that is around 2, okay? But then you put it in your body, which approximately has a pH of 7. Let's just say it's 7, okay? So which one is more acidic, a carboxylic acid or your body? Carboxylic acid, okay? And what does an acid do? It gives up a hydrogen, okay? So do you see here the hydrogen's gone? That means it's already reacted in your body, and that's how they're showing it. It's already acted as an acid. Now an amine has a pKa of about 15, 16, okay? And we're in a pH of 7, so which one is more basic? The amine. Now this normally would be NH2, but you see it's a positive charge. It has an extra hydrogen, because what does a base do? It accepts or takes a hydrogen. So it's already accepted an additional hydrogen, making it a positive charge. Okay, so this is after it's reacted. This acted as an acid, this acted as a base. And so whenever you see them with charges, that's what they're saying. If you see it neutral, which you see it like that all the time also, it just means it hasn't reacted yet. They're not showing it reacted. Which one's right, which one's wrong? There's really not a wrong or right unless they actually say it's at this pH, then they need to draw it correctly. But if you look at it, what if you'll go over this in biochemistry, different areas of your body have different pHs. For example, what about your stomach? I mean, you don't have to give me the exact pH, but is it acidic or acidic? Very acidic. It's actually going to be more acidic than a carboxylic acid. So at that point, the carboxylic acid is actually more like a base, sort of. And actually, it won't, because it is an acid, it won't actually react. But then there's parts of your body that are very basic, like in your kidney and stuff. So depending on where this is in your body, will actually change the structure. Okay? And all you need to do is compare the pKa's to each other. Oops. Here's what we're doing, the RDLS. So if we quickly go back to chapter 5, I think. So we have a CHO, an H, CH2OH, and an OH. Do you remember which one would have the highest priority? OH, with the oxygen. So the higher your atomic number, the higher the priority. Which one would be the lowest? H. Don't just ignore these numbers right here. They're just counting your carbons, 1, 2, 3. Okay, those aren't anything. So we have 1, we have 4, and here we have it doesn't look like it, but this is a C double bond OH. So this is an aldehyde right here. So what do you see here? So I have a double bond O, then I have a CH2OH, which would be a higher priority. The double bond O. So I have 1, 2, 3. So what does this look like? Clockwise or counterclockwise? It looks clockwise, but my lowest priority is on a wedge, so it's actually opposite. It's actually S, in this case, L. Okay? So this is how it's the same priorities, everything's the same. It's just instead of using RS, they use D and L. Most common in your body, you will find L. It doesn't mean that D doesn't exist. It's just probably, 95% or so in your body is the L amino acid. Okay? So now we're going to look at, so an amino acid is this individual compound. All right? but they don't usually exist as individual compounds unless you buy them that way, as like a natural product, some sort of, you could buy it in a container. Anyway, but usually they're bonded together, and when they bond together, these are called peptides. Okay? So you could join two different amino acids together. Now look here. I have a nitrogen and a carbonyl. Basically, this nitrogen is attracted to the carbonyl. So it's going to make a bond there. What happens to these electrons? They would go up, and they can come back down, and what would leave here? OH eventually is water as when it takes that hydrogen off there. So basically, these are joining together, and the leaving group is water. When you join two amino acids, they could be the same amino acid, they could be different amino acids, that doesn't matter. Okay? And so when you do this, you join here, and you make this amide bond, sometimes called a peptide bond. Do you see C double bond O, so that's our carbonyl, connected to an amine, this nitrogen. Okay? We call that an amide. So whenever you join two amino acids together, you form an amide, or a peptide bond. Now this is important. Your proteins in your body and a lot of your enzymes, these are long chains of amino acids. Okay? So whenever you refer to an amino acid, that's the individual unit. I'm trying to think of something that would make sense like that. I can't think of anything. Okay, so you have this individual unit. Whenever it's a small unit, like maybe 30 amino acids or less, they call that a peptide. Okay, when it's bigger than just the individual, but still not this huge chain. Okay, whenever they're proteins, this is hundreds and thousands of amino acids long. Okay, and these can fold, and you can get enzymes and stuff like that. Okay, so amino acids are very, very important. So again, these are the individual units, but they usually exist as large groups known as like proteins and enzymes and stuff. Oops. Now these can fold together, proteins. Now if that proteins do not fold correctly, this can cause different diseases like Alzheimer's, and stuff like that. So it's important that they fold together. How they fold is through hydrogen bonding. Do you see this oxygen attracted to the hydrogen? So here's one chain. Here's another chain of amino acids. And the oxygen of one is attracted to the hydrogen of another. And that's all protein folding is literally just hydrogen bonding. And if that's not folded correctly, if this chain over here, is somehow deformed, and then it tries to fold, it causes some major problems in your body. Okay. So that's amino acids in a nutshell. You'll learn more about them, but they're quite fascinating. And it's just an organic functional group. Okay. Whenever you're joining them together, it's just an amide. There's 20 standard. There's more than 20, but this is pretty much by far the most common amino acids, okay? And you see here L amino acids because those are the most common. So altogether, we're going to learn all 20. So what you'll want to know with these, and we're going to learn 2 today, is not only the name, so like glycine, alanine, proline, valine. So you want to know the name. You'll want to also know the R group. So do you see, if you compare these two, the top of this one looks exactly like the top of that one. Okay? This one's a little weird. I'll explain that one. Just ignore it so it doesn't confuse you. But it also looks like the top of that one. The tops of all of them are the same. Okay? Now, do you see this? What does it look like over here? Pinkish group here. These are your R groups. Okay? So, for example, glycine, the R group coming off of there is hydrogen. This one is methyl. Okay? And the final thing you'll want to know is the group that it goes in. Because Dr. Sarkar will also assume you know where they would fit. So do you see all of these listed here? This is not 20, right? This is just one group of the 20. These are the nonpolar aliphatic. Aliphatic meaning mainly made up of carbons. Nonpolar meaning not any kind of electronegative polar groups in there. Now what they're talking about, because you could tell me, if you look at here, you're like, well, there's 2 oxygens, a negative charge, there's a nitrogen with a positive charge. How are these nonpolar? Maybe you're thinking that. What they're talking about are the R groups, okay? Only the highlighted part there. So you see hydrogen, is that electronegative? No. This is nonpolar, and it's technically not aliphatic, but it fits better in that group than any other group. So really it's nonpolar. So all of these are your nonpolar. See, they're not charged. They don't have any electronegative atom groups in there. Okay, so I could ask you, for example, on an exam, name all of the nonpolar aliphatic R groups, okay? And you would have to list all of these, okay? Just to give you, I'm just throwing something out there. Or I could just ask you, draw the structure of glycine, and you would have to draw that, okay? So, know both ways. Okay, so the 2 we're going to learn today, the first one is glycine. And the R group here is just hydrogen. It's your most simple amino acid. And now look at this. Does this one technically have chirality? Is this one chiral? No, because it has 2 hydrogens. So this is the only one that's actually not chiral. I think they still refer to it as L-glycine, but it's not actually because it's not chiral. Glycine is used as a neurotransmitter. I'm just telling you this for your information. You don't have to write down if you want to. It helps sometimes if you're having sleeping problems. Glycine has been known to help. And they also use this sometimes as a sweetener to sweeten your food. So that's glycine. I'm sorry? They're doing the top one. Technically it doesn't matter, but it looks like they're doing the top one. And notice right here, they have these neutral, because it means it hasn't reacted yet. Okay, so the top one, technically in this picture, is your R group. You could have circled either one, though. And the last one we're going to learn today is alanine. So if we look at the top here, our R group is methyl. The only intermolecular force of this R group is dispersion, and that's going to be with all of these. There's no electronegative atom, and there's no hydrogen bonding. And again, they're talking about just that R group, not everything else. Yes? Not really. Unless they say to draw it in a specific stereochemistry, like to draw the D or the L, and that would be the only thing. Besides that, it doesn't matter. I don't care where you draw it. Alanine is used a lot for hypertension, and it's supposed to help with diabetes. I don't have any, never used it, but apparently studies have found that it is effective with that. So that's it. So glycine and alanine. So what's the R group for glycine? H, and alanine? Methyl. Okay. So tomorrow we'll learn 2 more. Okay, so we've learned for this new exam, Chapter 16, and the homework will help you with this, with aromatic, anti-aromatic, and non-aromatic. How do you know something's non-aromatic? What? It's non-cyclic. It's falls in carbons 8 through 13, and one of your carbons is sp3. Okay, it doesn't have to have all of those, just one of those to be non-aromatic. What's the difference between aromatic and anti-aromatic? The math, yeah. It's the 4n plus 2 rule, the Huckel's rule. So one ends up being a whole number, the other one is a fraction. Which one's the fraction? Anti-aromatic, yeah. And that just means it's unstable. You're going to have electrons that aren't paired whenever you get that. And then we have the nitrogens, if they're basic or not. How do we know if a nitrogen is basic? Yeah, the what about the lone pair? Yeah, you're not using the lone pairs, and how do you know if you're not, basically when you're counting them, how do you know when you're not counting them? The double bond. So if you have a double bond coming off that nitrogen, then it's basic, because then you don't need to count the lone pairs. So that is pretty much all of chapter 16. We also looked at a little bit of chapter 17. Let me just write these down. Do you remember what that put on benzene? Bromine? And let's also look at the mechanism of this. So there's the electrophile part of the mechanism and the benzene part. How do you make your good electrophile? What are we going to use? Yeah, you're going to use these two right here. What's sort of on the arrow there, that's what you're going to use to form your good electrophiles. So we have Br bonded to Br, and plus iron 3 bromide. And what did you say happens here? Yeah, bromine is going to join the iron. And then what happens next? Is this good? Is this the final step for this part? Yes. Now we have the benzene part of the reaction. Oops. And what does benzene make a bond to? Yeah, the non-charged bromine, which causes all of this to leave. So we have FeBr4 minus and what's the charge right here on benzene? Positive. And what is my final step here? I take off a hydrogen where? Yeah, where the bromine's at. And I'm going to use this negative FeBr4 to take it off. So grab that. And where does hydrogen leave its electrons? To make the double bond, which is our final product. All right, then we did one more. And what does that put on benzene? Chlorine. And how do we start the mechanism on this one? Yeah, we're going to have our chlorine here, and then our aluminum chloride. And then you said the chlorine is going to make a bond to the aluminum, just like the bromine did to the iron. Then what happens? The benzene. And where does benzene make a bond? Yeah, the chlorine right there. Causes all of that to leave. And the charge here, positive. And what is our final step? Yeah, we're going to take this hydrogen off and leave it as a double bond. So pretty much the same exact mechanism that we just did. Your next exam is only over 16 and 17, so only 2 chapters. All right, so on to some new reactions. One, 2, 3, 4, 5, 6, 7, 8, about 10. That's for the whole exam. It's not too horrible. I think that's less than last time. Okay, so the next one. Again, we start with benzene. Then over the arrow, we're going to put nitric acid and sulfuric acid. Sometimes this is called fuming sulfuric acid. Now this one, well, once I write the answer, it will be a little bit more obvious, but it's not as obvious just by looking at it. But what this puts on benzene is a nitro group, which is NO2. This is called nitrobenzene. Now, where does the NO2 come from? The HNO3, okay? But what do I need to lose here? An H and an O, which is an alcohol. What does an alcohol leave as? Water. But is alcohol the leaving group? No. What does it need to leave? Hydrogen to leave as water. Where do you think it's going to get a hydrogen from? Sulfuric acid. Usually sulfuric acid is in here on these reactions just to add a hydrogen to something. So we have, let me draw what HNO3 looks like. Okay, now this, I'm going to get it, I usually get this question. So the OH is what's going to grab the hydrogen. And why doesn't it the negative oxygen grab it? And technically it does. This will grab it. But then it'll have two OHs. Then ends up grab one of these, it doesn't matter which one, we'll end up grabbing another hydrogen, kicking the water off. Anyway, long story short, to skip all of those steps, we usually just show this oxygen in the end is grabbing the hydrogen. Because overall, that's actually what ends up happening, leaving as water. Okay? So this, and this will occur at the same time. Can this form a carbonyl if it kicks something off? Not, I say carbonyl, but can it form a double bond? Yeah. So just like forming a carbonyl, it wants to, and what does it want to kick off? OH. And this happens because this can leave and grab a hydrogen for that to occur. Now, this sulfuric acid was not in there. It would just stay like this. It's stable enough like that. Okay? But with this sulfuric acid in here to give up a hydrogen, it promotes this to happen. So this is all happening at the same time. This is pushing those electrons down, at the same time kicking off this alcohol there. So when I do that, what does this leave as? Water. And then this just HSO4 minus, because it lost one of its hydrogens. This will come in play here in a minute. That's why I'm writing it. So then that leaves us with NO2 and nitrogen with a positive charge. Okay, so this is our good reactive electrophile. Now, just like the other reactions we just did, now that I've made my good electrophile, what happens next? Benzene. Now, I told you the only part of the mechanism that we're going to do, of all of them that could change, is this part up here, this top part. But the benzene mechanism is always the same. So I have benzene, and I'm just going to write this as NO2. Is going to react with NO2. And looking at our product there, where does it make a bond? Nitrogen. And what's the charge of benzene right here? Positive. So you see exactly the same as we've been doing. Yes. Now the HSO4, that's why I wrote it up here, wants to reform itself to neutralize it. So that will take off the hydrogen right here to form the double bond, which is our final product. But do you see this benzene part of the reaction? Benzene attacks the electrophile, take off a hydrogen to form the double bond, which reforms benzene. That part is exactly the same, and it won't change. Okay, so that is one of our reactions. Now let me show you one more quick one. There's not a mechanism with it. I just want to show you this. So sometimes you might want NO2 on there, but other times you might want your amine on there, which would be NH2. Now if I go now look at the difference between the reactant and the product. What is the difference? Oxygen, right? We're getting rid of oxygen. Do you see that? And what are we adding? Hydrogen. So is that an oxidation or a reduction? Reduction. Now they do it one way. You could do it this way if you want. So one way to reduce this is zinc hydrochloric acid. The zinc causes a radical reaction. The hydrogens come from the hydrochloric acid. Or you could simply, and it doesn't have this listed, but you could do it this way, is just use your lithium aluminum hydride, which you're used to, which is your reducing agent. So I'm going to say or, either one. It doesn't matter. You see the same result. So that's a way to reduce your NO2, your nitro group. Your nitro, there's no way, there's no reaction really to put an amine directly on benzene. They don't know how to do that yet. I mean, like this. So the best, most effective way to do it is to put a nitro group on there, then reduce it. Okay? Why would you do that? I have no idea. Depends on what you're trying to make. Okay? So it's all, again, just a ton of reactions, and you decide when you want to use them. So let's take a break, and we'll learn some more. Mm-hmm. Mm-hmm. All right, let's go ahead and start back up. What I think I'm going to do is never mind. I'm going to continue on with what I'm doing. All right, so the next reaction, so we've learned two. We've learned how to put NO2 on there. Do you remember how to do that? HNO3 with H2SO4. And just as it's shown, how do I turn a nitro group into an amine? It's on here. Lithium aluminum hydride or zinc hydrochloric acid. So this is a oxidation or reduction? Reduction, because we're reducing oxygen. All right, the next one is a sulfonation. Okay, so let me show you what this puts on there. So where does this come from? The SO3, and where does the hydrogen come from? The sulfuric acid. So SO3 looks like this. And then we have sulfuric acid. Now, do you see one of these oxygens is going to grab a hydrogen? Do you think it matters which one? No, they're all the same. So I'm just going to use this one because it's closer. So it's going to grab a hydrogen, leave. Now, when you have, if you remember, when you have a positive on an electronegative atom, it's actually going to make what it's connected to more reactive because it wants those electrons back. It does not want a positive charge. Okay, so this sulfur right here is very reactive because oxygen wants its electrons back. So this is our electrophile. Now, what do you think the next part of the reaction is? Benzene. What is it going to make a bond to? Sulfur. And which electrons do you think go up? There is a right and wrong answer on this one. Which one has the positive? This one. So the electrons are going to go back to that one. Oh, and then we forgot this part. H2SO4 is now HSO4 minus. So I'm now going to write this as just SO3H at this point. And again, what's the charge right here? On benzene? Positive. And what's our final step? Make a double bond using what? And HSO4 so hydrogen. Notice the hydrogen is always where the group we just added was. HSO4 minus takes off that hydrogen to create the double bond. I guess I do change my mind now. Okay, so now we do this. Now let's move to ortho para. There's two other reactions that are similar to this, but we'll go over those either later or tomorrow. Because more importantly, let's now go over ortho, para, meta, because we know enough reactions to do that. Okay, if you remember, let's just say I have a branch coming off of here called X. Now, where is the ortho position? One away, so I'm just putting an O there. Where's meta? Yeah, next to that. And then para would be this one. And technically, both of those are ortho, both of those are meta. That one is para. X is your director, okay? Now, benzene by itself has no director on there. So if I put Br2, FeBr3 in there, what does that put on benzene? Bromine. And at this point, there's nothing directing it, so you can put it anywhere on benzene, okay? So I can put it over here if I want, or somebody could put it here or there. It doesn't matter. There's nothing directing it. It can go anywhere. But if we have a director, and I'm going to go back to just X, and I will have to show you how to decide what type of director it is. But what if I tell you it is a meta-director, okay? We're using the same reaction. So if I'm using this over the arrow, what am I putting on benzene? Bromine. So I'm putting bromine on there. And I'm telling you this is going to be a meta-director, okay? So where do we have to put bromine now? Yeah, in one of the meta positions. Now, it could be either one, but it cannot go here, here, or there, because those are all your ortho-para positions. So X is still on there. We did this. Does that take X off? No, all it does is put on a bromine. And then we put on a bromine in the meta position. So what goes over the arrow tells us what we're putting on, and then the director will tell you where to put it on. Now, I'll remind you, this has no director, so you can put it anywhere. This one has a director, so you have to put it in a specific area. So now we need to look at how do we know where the director will direct it. Here you go. Now this one here, it tells you it's a ortho-para director, okay? So let's see, what am I putting on there? This nitro group, this NO2. What is on there initially? Methyl. So it tells you methyl is a ortho-para director. Now, I'll give you a shortcut on how to do this, but let's look at why. So this, if we're looking at our benzene reaction, benzene is going to make a bond to the NO2. Okay? Now when it does this, it puts your NO2 right there, and then one away where the other double bond, where the other side of the double bond was, where we have our positive charge. Right? That's part of the mechanism we've been doing today. Now remember resonance. We can stabilize this. So do you see when I put a positive charge right there, I now have a tertiary carbocation. See, 1, 2, 3 bonds to carbon coming off of this point there. is tertiary favorable? Yeah, the most stable is the tertiary. And so it makes this very stable carbocation. Now you can move it around. If I move this double bond there, that puts the positive right there in this picture, which is now secondary. Then I can move this double bond there, which puts a positive there. Anyway, the point is, here I have a tertiary carbocation. These are secondary. Are these a stable? No, but that doesn't really matter. Can at some point I make a very stable carbocation? Yes. And this is when you put it, do you see, here is my director, and I'm putting NO2 one away, so that is the ortho position. Now let's look if I put it in para, which would be down here. So if I put NO2 right here, that means my positive charge is right there, right? So I put my positive right there. What type of carbocation is that? Secondary, right? That's not the most, it's not terrible, but it's not the most stable. Now I can move this double bond there, which would make the positive right here. Now right there, what type of carbocation did I make? Tertiary. So both with the ortho and the para, did you see that at some point when I moved the electrons around, I could make a very stable carbocation? It doesn't matter that it took a little bit more effort to do this one than that one. It doesn't matter. As long as you can make it at some point, it's stable. Okay, now let's look at why this would not want to go meta. Okay, because it says it's an ortho para director. You can see it forms a stable carbocation, so that's the driving force there. But let's look at meta. So meta would be a 2 away, or 1, 3 if you want, right here. So I would put NO2 right here, and my positive charge right there. Now they move the electrons all the way around. You see here, here, here. Do I ever make my tertiary stable carbocation? Now you see secondary, secondary, secondary. So if I had to choose, I have a choice. I have a choice between all three. Which one would I rather go to? That would be the most stable. Ortho-para. And meta would be the least stable out of them. So that's why this ends up being an ortho-para director. Okay, so the driving force is stability. Now, I'm going to show you a shortcut so you don't have to do the resonance every single time. But just know, even when I show you the shortcut to this, the reason it'll go ortho-para versus meta, or meta versus ortho-para, is that that position is the most stable position to form your carbocation with resonance. Okay, so looking here, let's rationalize this. This is a carbon group. So every carbon group, it doesn't matter if it's methyl, ethyl, propyl, butyl, isobutyl, that doesn't matter. If it's just carbons and hydrogens, they're all going to be ortho-para directors. Okay? So looking at this, what does this put on benzene? Bromine. And then this will direct it ortho-para. So if we look on here, let's look at our results. We have 38% ortho, 62% para, and less than 1% meta. So why not meta? It's not as stable. Okay, and we can see that from the results. Reactions always go to greatest stability. So now let's look at these two. So these are definitely our major products here. So if I gave you this reaction here, you have to draw both the ortho and the para. Okay? And now you don't have to give me approximate percentages because you have no idea until you do the reaction. But let's rationalize this one though. Why do you think para is a little more stable? You can see it's more stable because you form more of it than ortho. Yeah, the sterics, which would be the spacing between them. Do you see this one's a little bit more crowded? So do you see they're closer together? Versus this one is like 180 degrees apart, basically. So because of that slight difference there, para usually, not always, usually ends up being the more stable one. Ortho-para directors, are called activators, meaning they activate benzene to become more reactive. Now let me show you how you can, so benzene by itself, is it that reactive? No, because it's stable. But if you put a ortho para / activator on there, now it's all of a sudden like 10,000 times more reactive. Okay? Now, with the reaction for lab 5, we had phenol. Now that one was very reactive, so I would have called that activating. And if you look on there, it goes to the ortho para positions. Okay, so now let's look at how can you tell just by looking at it if it's going to be ortho para. So we have ortho para. It's activating, meaning benzene is now more reactive with it on there. And what you look at, let's do a couple of examples. So let's just look at methyl. Look at the atom directly connected to benzene. So which is what? Carbon, right? Is carbon connected to anything more electronegative? No. So then it's called a ortho para director activating. So this is the most electronegative atom directly connected here to benzene. And so what it will do, any of its electron density, it will actually donate into the ring. If it can donate into the ring to activate it, it will. So if we look at the one in the lab, phenol. So what is the atom directly connected to benzene? Oxygen. Is it connected to something more electronegative? No. So that would be ortho para activating. It's going to donate electron density. Now versus if I have something like this, like NO2. What is directly connected to benzene? Nitrogen. Is it connected to something more electronegative? Yes, so that oxygen is actually going to pull electron density out of there, away from nitrogen. So if these are activating, this one would be deactivating. Deactivating meaning it's now going to make benzene even less reactive than you started off with. So benzene by itself is already not very reactive. Now if you put a deactivator on there, it's even less reactive. It's almost impossible to react. So we can have, let me give another example, like this is how you get meta. Let's look at this one. What is directly connected to benzene? Carbon. Is carbon connected to something more electronegative? Yes. So what would that one be? The deactivator. Which we'll find here in a minute that will end up being your meta director. So does it make sense how to tell the difference? Just that quick little test there will give you the answer. So let's go to when we looked at ortho para, what was the driving force? Why would something go ortho para versus meta? Stability. So why do you think something will go to meta versus ortho para? Stability. Here. So let's look at this. What's directly connected to benzene? Oxygen. And is it connected to something more electronegative? No, so that would make it ortho para. Now, if you look here, so you see that in the resonance, I actually am able to take the positive charge out of benzene. If you can take a positive charge out of benzene, that's the most stable you can make it. Okay? Now, you might want to know when can you do that and when can you not. Do you see the atom directly connected here is oxygen? Do you see how it's lone pairs? Then it will be able to take a positive charge out of benzene. Really, the only ortho-para director that can't do that is a carbon group. Carbon group never has lone pairs. But oxygens, nitrogens, those always do. So these are called pi donators. Pi meaning like a double bond. So you see right here when it takes the positive charge out, what do we form here? A double bond. So if you can form a double bond, bring the positive charge out, that's called a pi donator. And again, pretty much everything but carbon is a pi donator. Then we look at meta. So meta here, are we ever able to make that double bond oxygen with a positive charge out of the ring? No. So again, the driving force is stability. So I think the next one is finally a meta. No, it is not. But we'll look here. This one's actually very similar to what we did in the lab. Okay? We said this is what we just did. This was a ortho-para director. Now is this, so we call it pi or sigma donator. Pi meaning you have the lone pairs to make that double bond. Sigma meaning you can't. You can only have single bonds, which would be with carbon. Now is this a pi or a sigma donator? Pi, because it can make the double bond, basically it has lone pairs. Lone pairs equal pi. So it's the most stable you can make it. So that would make it the strongest activator possible. Okay, just kind of like with your OH. OH and alcohol, does that oxygen have lone pairs? All oxygens are going to have lone pairs. So yes. Okay, so just if this was phenol, it would also have the same ability to do this. Now here they put excess bromine. They actually said 3. In our lab, we just put a ton in there to overwhelm it. Okay, now look, where does the bromine add? Every single ortho-para position. Now, is this an activator or deactivator? Activator. So it has the ability to add to every single position if possible, and you see 100% of the product is this. So if we write down, so we have our summary. Ortho-para is always activating, makes it more reactive. If you're a pi donor, you have lone pairs. And I'm going to put in parentheses to make double bond. If you are a sigma donor, that means you have no lone pairs. And then just so you know, this one is the strongest. These are the strongest activators. Okay, so meta. Here's a summary of activators. You don't need to memorize these. Again, I don't like lists. You can tell by looking at them, right? So if nitrogen was connected, so this line means it's connected to benzene. Is it connected to something more electronegative? No, so it's ortho-para activator. OH, oxygen, is it connected to something more electronegative? No. OR, is it oxygen connected to something more electronegative? No. And let me show you this one. Nitrogen, is it directly bonded to something more electronegative? No, so it's still an ortho-para director. I know it has an oxygen there, but it's not directly bonded to it, so it won't affect it. Okay? So these you don't need to memorize. If you understand the shortcut and how to do it, then you're fine. Okay? No need to memorize something that you already know. Okay, let's look at this one. I have a nitrogen here. Is it connected to something more electronegative? Yes, that makes it a meta-director. And if we look on here, let's look at our results. Well, before we do that, HNO3, H2SO4, what does that put on benzene? NO2, another NO2. So this NO2 will direct the next NO2 to meta. So if we look at this, ortho is only 6% of the product, meta 93%, para 0.7%. Okay, so this one right here, the 93%, do you see their meta, the relationship there, 1,3, is the most stable. So let's look at the resonance here. Here, this is interesting. Nitrobenzene is 100,000 times slower than just regular benzene. Just to give you an idea of how slow a deactivator makes the reaction. Okay. Now let's look at this. I put whatever electrophile I'm trying to put on there, whatever group, doesn't matter. Now let's look at, they have ortho first. Ortho would be right here, which would put my positive right there. I have a positive next to a positive. Is a positive attracted to a positive? No, they repel each other. This is about as unstable as you can get. So because this forms basically this extremely unstable carbocation, it just won't even go, just because it's one of the possibilities. Now if we look at, well, I don't think it actually shows it, but para, if you put it down here, would also make, as you move the electrons around, this really unstable carbocation. Have a positive next to a positive. Now let's look at the meta. Meta would be putting it right here. So let's see, the first time I have a positive right there, which is what type of positive? Primary, secondary, tertiary? Secondary. So I have secondary, not bad. Do I have the really unstable one? No. Let's look at this one. Is it next? Is it directly? No. It's secondary, but it's not the most unstable. And then this one over here? Secondary, but is it bonded right there to the positive one? No. So basically the driving force is it's the lesser of the two evils, right? No, you never make a tertiary carbocation, but at least you don't make a positive next to a positive. And so that's why the driving force will be meta. So it goes down to stability again. The driving force with anything in this chapter, and really all of organic chemistry, is stability. Which one forms the most stable, in this case, carbocation? All meta-directors, doing our shortcut, will always have this sort of resonance here. And so you can go on and look at all of these. Let's look at, for example, sulfur. Is it connected to something more electronegative? Oxygen is more electronegative. So that would be a what type of? Meta-deactivator. And then we'll just look at one more right here. Is carbon connected to something more electronegative? Yes. So that is a meta-deactivator. Okay, so this is just a list. Again, don't memorize that. Now the last group, so we have orthopara activating, and then we have meta. These are always deactivators. Then we have this special group called halogens. Now, what is the most electronegative atom on the whole entire periodic table? Fluorine. So all of your halogens have this unique ability to mess up benzene, okay, because they're very electronegative. So let's see what they do. Now, I'm giving it its own group because it's sort of halfway in between meta and orthopara. It doesn't really go in either of them. So let's look at the results here. I have chlorine on there, so that's my director. So whatever is on benzene at the beginning, your reactant, that's your director. Now what am I putting on here? NO2. Now based on these results here, what type of director is it? Ortho para, right? Definitely not meta. We only have 1%. Okay, so I have on here halogens are ortho para directors. The reason they're ortho para directors, if I just have chlorine on there, is it connected to anything more electronegative? No, it's by itself. And then these always have lone pairs, and so they can kind of bring into the ring there. So it's ortho para. But because they're so electronegative atoms, what are they attracted to? Electrons, right? So it's trying to pull all of the electrons towards itself. So this, even though it can do all of that, at the same time, it's also fighting that and pulling electrons away because it is so electronegative. And so it actually ends up being a deactivator. So would this make the reaction more reactive or less reactive? Less reactive. So halogens, though they are ortho para directors, and you usually associate that with activating, it's a special case. They're so electronegative that actually they end up being deactivators. So where this comes in, we'll be practicing like this. If I have this. What is my director? NO2. Right. This part here is my director. This is just what I'm putting on benzene. Okay? It doesn't direct, has no influence on where it goes. So NO2, what type of director is it? Ortho para or meta? Meta. So what are we trying to put on benzene? Chlorine. So where will I put that? Meta, but where's meta? 3 over. Or 2, however you want to look at it. It's that position. So my NO2 is still there, and then I just put on chlorine. Now let's think of this in a backwards way. Let's just go ahead and make it hard, right? Yes. Everybody loves to be mentally challenged. Let's keep it up here. This is SO3H, it's connected weird, but whatever. I'm making that. And I'm starting, I'll even give you what we're going to start with. Benzene. Yeah, we know how to put these on. How do I put HSO3? I mean, you might not have it memorized, but looking through your notes, how do I put that on there? Yeah, SO3, H2SO4. And NH2, can I put that on directly? No. What do I have to put on first? NO2, so I'm going to put like step 1, HNO3, H2SO4. And then how do I actually turn that into NH2? Lithium aluminum hydride work. Okay, so those are the things I'm going to put all over the arrow. But it matters what order I put these in. So what is the relationship between the two branches? Is it para, ortho, meta? They're para. So what type of director do I need to put on there to do that? Ortho, para. Now, between the two that are on here, which one's ortho, para? So this one, nitrogen, is it connected to something more or less or negative? No, so what type of director is that? This one's ortho, para. Sulfur, it's actually sulfur connected. Okay, if you want, that's the bond. Is it connected to something more electronegative? Yes, so that would make this meta. Now, these we said are orthopara, right? I mean, they're para. So I need an orthopara director. So which one will be my director? NH2. So I need to put NH2 on there first. So I already put on how to do that. I need a step 1, HNO3, H2SO4. In step 2, I said lithium aluminum hydride. And then that would put on NH2. I'm just writing what I wrote there in red. Okay, now what do I put on? Yeah, how to make H2SO4. So that would be the SO3 H2SO4. Now let's pretend I reverse this. What if I put this here and that there? What type of director is this? Meta, so I would have put that on there, which would put SO3 on there, SO3H on there. But then where would it have put the NH2? Yeah, it would be the meta position 1 over. And do I want the meta position? No. So how you rationalize, this is how I always do it, the order, and you can do it whatever order you want. But I like to first just write down how do I put those groups on there. So I just have that as a side note. You know, this part is just memorization, really. Then I look at what's the relationship between the two. Are they ortho, para, meta? Because that will tell me which director. Now let's say they're both ortho, para directors. Would it matter which one I use first? No. I cannot give you one that has 2 meta directors and all of a sudden you put it on ortho. Okay, that wouldn't work. But I know these are para, so I have to use that director. That means I had to put that one on first. So the relationship tells you which group to put on first. And we'll do more of those tomorrow. I have your exams. Let me actually pass those out tomorrow so you have more time to look at them. I forgot I had them. It's at the end of this chapter. What NBS does, it puts a bromine, 1 carbon coming off benzene. It puts a bromine, NBS is a form of bromine, 1 carbon away from benzene in the most stable position. So you have these here. So 1 carbon away would be here, here, and here.
Okay, but not here because
it won't go there. It already has 4 bonds. Now you have to choose between here and here, and it's going to go to the most stable, which would be the secondary, the most branches.
And then permanganate and alcohol?
What that'll do, it turns any, and these will all react, any carbon group into a carboxylic acid.
So any of these become a carboxylic acid?
All of them will.
Every carbon or just the...
It literally cleaves it and turns them into a carboxylic acid. So coming off of there, let me draw it on there. It doesn't matter how big the carbon group is. I don't remember what you had. Something like that. Basically what you'll have then is that. And it only does that to carbon groups. So if there was a bromine on there, it wouldn't affect it.
So the one is just basically, so a methyl turns into the carboxylic.
Yeah, it cleaves everything off except that first carbon and oxidizes it.
Oh, I see. So all those carbons leave,
Uh-huh.
and then we just got carboxylic acid all over.
Correct. And it doesn't matter how big that carbon group is. That doesn't matter. Yes. These down. Thank you.
Thank you.
Can I give you Fred taking pictures of it?
Yes,
Since
you
I
can.
have it?
Yes.
I haven't done the video yet, but it's due tomorrow.
Yeah. Yes, it's due tomorrow at midnight.